Hello everyone, my name is Luisa Pätzold and I'm currently a graduate student at the Bonn-Rhein-Sieg University of Applied Sciences. Thank you very much for having me. I'm here today to talk about the work we did on performance and scalability evaluation of real-time mesoscopic persistent agents. And I worked on this topic together with my colleagues Sven Seele and Professor Herpers at the Institute of Visual Computing. So without much further ado, let's get started. At the Institute of Visual Computing, one of our main research areas are virtual environments. And they are a great tool for training, simulation, games, and more. And one way of making them more immersive, plausible, and realistic is by adding intelligent virtual agents. And of course, I don't have to explain the advantages of them. And I'm sure that you're also well aware of the fact that more complex behavior means also more processing power, especially if many agents have to be simulated. And that is why in larger applications, intelligent virtual agents that leave a user's proximity or the field of view are removed from the simulation. And this saves resources, but it can lead to inconsistent situations for the user. For example, if agents have evolving characteristics, their state is lost. And this approach may be a feasible solution, but only if a user's attention is not distracted by this lack of persistence. And by avoiding distracting inconsistencies, the feeling of immersion can be improved and also the experience can be enhanced for users. And as mentioned before, a continuous simulation is required if agents have evolving characteristics that, for example, influence their behavior. And one possible solution to this problem that we explored is to simulate agents using different levels of detail. And that is comparable to the level of detail approach in rendering, where distant objects are replaced by 3D models with less resolution to decrease the render times. And in the case of agent simulations, this means only specific subsets of their functionality are actually continuously simulated. Our specific use case for this scenario is the Phoebus bicycle simulator. And the most relevant fact for this presentation is that it is an immersive learning environment for road safety. And in order for that to work, we need intelligent traffic agents that emulate human behavior in traffic. And this requirement by itself is a challenge, but we also have to simulate a whole lot of these agents to interact with a trainee. And if a trainee encounters the same agent multiple times, their behavior should be recognizable. And that's where the persistence and the level of detail requirements then come into play. A former colleague looked into these approaches and he described a mesoscopic traffic simulation layer that tracks agents and their evolving characteristics throughout our entire traffic network, even when they are not visible to a user. And more on this mesoscopic system and the level of detail approach later. The system was then applied to the Phoebus bicycle simulator and evaluated as such. And now we wanted to find out whether that system could also be used for more generalized cases. That means larger traffic networks than the one investigated before, but also perhaps other interactive environments unrelated to traffic. And in other words, could we use the system to extend some other environment for intelligent virtual agents to make it persistent and maintain interactive frame rates? And that means we extended the original evaluation by investigating larger network sizes and larger agent populations. We monitored the system's performance and then we interpreted the results. First of all, what does the system actually look like? Around the trainee, agents are simulated microscopically. And this microlayer here on the left side is split into two further sections. First, and the intelligent virtual traffic agents, including all implemented features, they are simulated within a user's immediate surroundings for most detail. And once these agents move further away, a simplified but still visible agent type is used instead. And then, once agents leave the user's field of view, they are transferred to a mesoscopic simulation layer here on the right side of the image. A mesoscopic simulation layer lies between a microscopic simulation that simulates each individual entity and macroscopic simulations, which simulate aggregated parameters and entity collectives. And microscopic simulations are required to investigate details, while macroscopic simulations are needed for large scales, typically to save processing resources. And mesoscopic models apply computationally inexpensive approaches while still maintaining associated information, such as route choices, vehicle type, and in our case, personality profiles. And the investigated system uses a queue-based model inspired by the fast lane traffic model to simulate agents within the specified layer. And that means each road is represented by a priority queue, as you can see down there, a priority queue for each driving direction, for which the key is the agent's time to destination. And this time depends on an agent's velocity preference, as well as the length of the road, and it decreases over time. And once it reaches 0, which means the agent has arrived at the end of the road, a routing choice is made. And then the agent transfers into a first in, first out queue. And there's one such queue for each connecting road. As mentioned before, routing choices can be part of the agent, but for the simulation, they were just decided at random. And at specific intervals, a certain number of agents are then allowed to transfer from their queue to their designated road. And the number of agents here can vary. But if the next road is full, the agents cannot transfer, but they must wait for the next simulation step, which is a spillover effect. And these different parameters are used to simulate turning maneuvers, right-of-way priorities, agent-to-agent interactions, and so on. And obviously, the traffic network can have any shape, but for the evaluation, an n times n grid structure was chosen because it can be easily extended automatically. And this figure here shows a 3x3 example. Each node or intersection is connected with its immediate neighbors in both directions. And to increase the network size, we just added a certain number of rows and columns. For our current evaluation, we performed 3 experiments. In the first experiment, we started with a network size of n equal to 2, and then increased n with each run by 5, up to n equal to 92, or 8,464 nodes. Then we simulated each network with an agent population of 10 to 100,000 agents. We started with 10, increased that to 5,000, and then, starting at 10,000, we increased the number by 10,000 until 100,000 agents were reached. And the maximum number of 100,000 agents was the same as in the original evaluation, but the maximum network size was already much larger. As I mentioned, 8,464 nodes instead of just 625. But we wanted to push that even further, so we took the 100,000 agents and then simulated them in networks from 4 to around 16,000 nodes, as well as 30, 45, and 60,000 nodes. And as a comparison, the road network of the city of New York City consists of about 50,000 intersections, while Glasgow has about 12,000. And we also chose one network of about 16,000 nodes and simulated 500,000, 1 million, 1.5 million, and 2 million agents in it. And as shown in the example before, the network was always laid out as an n times n grid. And each simulation was run for 2 minutes, and then the time it took to calculate each frame was aggregated over 1 second and logged into a file. And then we performed the simulations on a consumer level PC with these specs you can see down here on the slide. So here you can see the results for the first trial. For network sizes from 4 to about 8,500 nodes, and with agent populations from 10 to 100,000 agents. And for each line, the figure shows the median calculation times across the 2-minute simulations. And all runs show a linear increase for increasing network sizes, which is what we anticipated. There's something else going on in the beginning for very small agent populations, but afterwards that becomes linear as well. And such small populations are not really a meaningful use case, so this should be negligible. Second, all configurations in this trial could be simulated in real time, which we define to be above 30 FPS or below 33.33 milliseconds calculation time per frame. We did, however, notice one interesting observation. That is, with increasing network size, an increase of the number of agents seems to grow non-linearly, as we can see here on the right side of the plot. So going further, we wanted to test 2 things. First, the limits of the system with regard to interactive frame rates and the growth of computation times for increasing agent populations in a large network. So first, let's take a look at the growth behavior for even larger networks to investigate the possible use for other applications, such as current open world games. So we simulated a population of 100,000 agents in networks of up to 60,000 nodes. And as you can see, the linear growth can be observed here as well. Unfortunately, regarding real-time capability, we observed that the system quickly reaches its limits. And in this case, a maximum of 15,000 nodes can be simulated in real time. Remember that the city of Glasgow has a traffic network of about this size. Another example is the city of Cologne with around 13,000 nodes. And granted, these are still fairly large cities if you consider applications like virtual environments. For example, in the latest Spider-Man game for the PlayStation 4, New York City's district Manhattan is the traversable world. And the about 4,000 intersections of real-world Manhattan's road network are well below our threshold. However, if this system was to be a part of a larger system, like for example a video game, only a fraction of the available processing power would actually be available for the mesoscopic simulation. If we had a specific number for that, we could use a graph like this to find the maximum possible size of the network. But we wanted to take a look at the agent population as well. And here you can see the median calculation times for a traffic network of about 16,000 nodes, with agent populations from 10 agents to 2 million agents. I mentioned earlier that the first trial suggested a nonlinear progression of calculation times. And the same can be observed for this network size, but only in the beginning. After that, you can see that it does grow linearly. Unfortunately, as seen in our previous trial, the limit for real-time calculation is also reached quickly, in this case at 100,000 agents. And as I also mentioned before, this also assumes that all processing resources go into the mesoscopic simulation, which is an unlikely application scenario. But again, 16,000 nodes are probably a pretty large network, and in smaller networks, that threshold would lie above 100,000 agents. So, in conclusion, in our contribution, we extended the evaluation of the mesoscopic simulation by our former colleague to evaluate its scalability and whether it could be applied to larger traffic networks. Furthermore, we examined the possibility of other use cases of the system, for example, for more general simulations in open-world virtual environments. And with this evaluation, we showed that the system quickly reaches its limits regarding network size and agent count when interactive simulations are required. And for a population of 100,000 agents, that threshold is reached below 15,000 nodes. And if the system was to be integrated into a larger program, like a digital game, that threshold would lie even lower. And therefore, we have to conclude that the mesoscopic simulation in its original form cannot interactively simulate traffic networks of much larger sizes, which would be required to simulate, for example, a metropolis or even an entire country, such as Switzerland with over 200,000 nodes. And now, these conclusions might sound discouraging, but since the system was not originally developed for traffic networks of these dimensions, there are many opportunities still for improvement. And further work on optimization could decrease the growth and therefore might allow larger networks to be interactively simulated. For example, the mesoscopic agents are currently still simulated sequentially. However, our approach would lend itself well to parallelization. And generally, we are convinced that it would be worth looking into possible optimizations, as simulating persistent agents remains a promising idea. And with that, I come to the end of my presentation. Thank you very much for your attention.